On December 9th, 2021, I was privileged to address this National Advisory Board again after making two earlier presentations in 2015 and 2018. As I said in those earlier years, our air traffic control system's collision avoidance capability is glaringly inadequate for future traffic density. Now there's an added sense of urgency. We're about to have large numbers of things flying through the air without a pilot. The word drones is a misnomer, but we'll use it as everyone else does. Even with just a few of them in the air, they've already collided with passenger aircraft. In years to come, those few drones will grow from dozens to hundreds, then to thousands. And some of those will be rogues, or swarms of rogues. We can either get to work on this, or we can find ourselves feeling like we're surrounded by crocodiles. Before my turn to speak, there were more excellent presentations than I have time to cover here. Let me just mention some primary highlights. Father of GPS, Brad Parkinson, offered a status review with recommendations, noting specific areas where improvements are long overdue. RNTF President Dana Goward narrated several disasters that occurred after warnings were ignored. Logan Scott gave the latest update on authenticating satellite signals. Captain William Cotton stressed the necessity to automate air traffic management, ATM, decisions that are far beyond any human capability. I could not have invented a better setting to fit in everything I need to say. A logical introduction can start with this document, in the works for a few years now. Its latest version continues to declare a deficiency that's critical, so action is mandatory. In stepping up to this challenge, SAE International doesn't claim unique capability. There are other pockets of expertise, but they're distributed. You won't have everything you need from one place in a consistent form. Different groups give information in different ways. Immediately, that means you won't get interoperability. And without that freedom to replace one unit by another, you'll never control the costs. That's especially true when proprietary rights are taken to extremes. Proprietary mechanizations are acceptable, no problem with that. But extending those rights to cover common knowledge obstructs not only affordability, but safety. SAE International will establish standards to require availability of measurement data and to furnish information enabling effective usage of the data. This was the theme of my message, hazards ahead. Even without those drone collisions I mentioned earlier, and even without drones for delivery or air taxis, the internet showed near-miss events. Scary. You could say they weren't officially recognized, but it's reckless to ignore those. Also on the ground, we passed the mark of 1,000 annual runway incursions years ago. Clearly what we have is not enough. Of course, we cannot just discard our air traffic control system, but we do have to add something. Fortunately, there's a straightforward way to make the addition. It really is important to see that the vital step Captain William Cotton identified is 100% realistic. By capitalizing on methods not currently used to manage air traffic, we can get dramatically improved performance. The key is a vast difference between positioning and position-dependent measurements. If that just sounds like semantics, think again. In 1959, Coleman underscored the huge significance of some measurements being more accurate than others, much more sensitive in one direction than another, plus statistical correlations everywhere. There are correlations between estimation errors, across axes, across time, between position and velocity components, etc., etc. Existing ATM forfeits all that added information and provides just positioning, like a trail of breadcrumbs, treating them all alike and independent. So, look at all those things you're unable to do. No tight coupling, no integrity test, no differential operation. What does ATM need? Measurements, not coordinates. That enhances maintenance of a separate dynamic file for every tracked object. Just a couple of links are shown. The first presentation where I emphasized raw data was NACON 77. My 2015 presentation, cited on the first slide, gives references going back to then, and I've been harping on it ever since. Not to act like a parrot, but limitations of positioning are fundamental, intrinsic, and severe. I mentioned dependencies across time. Why should we care about that? The answer is absolutely crucial. Collision avoidance depends on where we will be later, at the time of closest approach, and relative to other objects, which has to include all other objects, because obviously we cannot afford to collide with any. But positioning reports just give instantaneous, not future location, with respect to a terrestrial reference, not relative to objects coming toward us. Could we derive future separation from that? Only very crude. Without seeing individual measurements, we're unaware of variations in accuracy, sensitivity in different directions. We lose opportunities for integrity monitoring to reject questionable data. And since measurements used by other participants can always include some not used in our own NAV solution, we sacrifice cancellation of common errors by differential operation. The next image shows how huge that loss can actually be. Consider a scenario with a little over 1.5 minutes to closest approach. The journal publication described a flight test from April 2012. Residuals over 1 second intervals consistently indicated 1 centimeter per second velocity accuracy, orders of magnitude better than anything available from methods in current use. The videos cited described ways to use the information for tracking and collision avoidance. After 100 seconds, a centimeter per second velocity error produces just 1 meter of position uncertainty, and therefore 1 times 1 equals 1 square meter of uncertainty area projected ahead to closest approach. Now for comparison, a 10 meter per second velocity error value can be found in ADS-B literature, not vectorial, not relative, and without strong statistical overtones. Anyway, if we again project ahead and square the result to get area, that number in red is rather significant. It could be argued that the outcome was somewhat idealized. Suppose practical conditions made the factor of 1,000 off by an order of magnitude. If so, then maybe instead of 1,000 times 1,000, we get 100 times 100. Improvement by a factor of only 10,000 in area. Only 10,000 times better. A point often overlooked is separating motion of CG from motion with respect to the CG. For example, due to rotations that distract observed motion of receivers displaced from CG by long lever arms. Dynamics can be best modeled at CG, from CG to CG. Before transmitting, sat-nav measurements should be re-expressed as values that would have been observed at CG. And before forming differences, the lever arm should also be extracted out from measurements at the receiving end. For those interested, A dramatic example of separating CG motion is given in the video at the link shown. Unlike TCAS, which enables accurate velocity determination along range only, the April 2012 flight test had three-dimensional information from measurements in all directions. Here's how precise streaming relative velocity vectors can provide safety. Think of a sea captain seeing another ship always appearing from the same angle. Zero line of sight rate indicates a collision course. He could either speed up or slow down. He can decide which, and with accurate velocity, how much. The amount will depend on his increase or decrease decision and speeds and geometry. So would the difference between time to closest approach and time to go. That is the ratio of range to range rate. Examples are plotted over a 100-degree span of intruder course directions. They cover many geometries, but not all. Low aspect will require turns, but not climb and dive. Advantages over TCAS are as dramatic as they are obvious. With accuracy along range only, accurate cross-range knowledge evolves slowly. It has to wait for sight lines to rotate, which happens only at short ranges, exactly what collision avoidance is intended to prevent. So by the time TCAS knows enough to make a decision, it's an emergency. Also, a measurement-based scheme can be used on the surface as well as in air. Now expand the scope to include a crowd. As participants receive squitter messages from each other, each can maintain separate track files for all others. That much is like ADS-B, but using the same hardware and the same message formats, just replace positioning with individual measurements. Each track file can use whatever information is received in common to update position and velocity, now precise and relative, every second. If all this is too time-consuming, a very short video offers a summary. In putting this report together for SAE, I had vital inputs. Look at the names on that roster. A rompin' stompin' all-star team. All of those people have the highest qualifications, obviously. Here there's time to mention details about two of them, Ogun and Logan. Ogun is Major Ron Ogun of Civil Air Patrol, who contributed an enormous amount of information on what to do about ADS-B. Logan is Logan Scott, who knows so much better than I could ever describe all about authenticating satellite signals. Just one item I'll mention on that subject. Yes, we will need bandwidth for that. And as long as we'll be taking more bandwidth, let's investigate the impact of shared measurements instead of coordinates while we're at it. If FCC won't cooperate, then we can't have safe transportation. But Joe Blow from Kokomo can have streaming video on demand for entertainment. Someone with authority I lack might want to shine a bright spotlight on FCC's priorities. One more item from that SAE report is mentioned here. Constant monitoring of speed, altitude, and dive angle enables ground collisions to be predicted. An automated pull-up command is credited with saving lives of unaware F-16 pilots. The design is clearly excellent. My only comment is that, with a solid basis in physics, there is nothing artificial about it. AI is very good at what it does, but it can create a temptation to use it where it's needed and also where it isn't needed. If it can be used for everything, then supposedly no one has to think. Our industry already has seen enough triumph of expediency over thought, even without AI. Witness the continued popularity of loose coupling. The objective should be to recognize extraction of maximum benefit from a combination.
speed from the computer plus rational judgment from a qualified analyst. I would not categorize automatic pull-up as AI.
Okay, ATM urgently needs improved algorithms and software, as just emphasized. Dead serious about that. Still, if that were the only thing being recommended, I might as well be just whistling Dixie. In order to be effective, the intended instructions have to take place in hardware, with all signals present each at the time intended. With the high data rates involved, that imposes accompanying demands. Two examples include cabling, that has its own set of strict standards, and computational construction of a unified time base from independent subsystem clocks. Outputs of each device can be delayed until it's in sync with the slowest. Then data to be mixed will have times that match. With good design, that slowest latency is brief enough to allow compensation by extrapolating the mixed outcomes up to present time. These things are more easily said than done. One with decades of hardware experience in operational environments is the next speaker, Bill Woodward, chair of SAE International's Aerospace Avionics Systems Group. Subsequent discussion included mention of industry reaction. Brad Parkinson noted, correctly, that existing ways of sat-nav inertial integration are quite useful, and incentives for development should continue. This does not in any way conflict with the dramatic change in direction being proposed for ATM. The reason follows instantly from that 2012 flight test with centimeter per second accuracy. Inertial data played no part in that success. Aircraft had no access to any IMU except their own. So track files were maintained by sharing GPS data only. That's been the point of this entire presentation. Differential operation for relative states, whether the longitude is 30 degrees or 130. Earth reference matters far less than separating from other objects. We worked by comparing not coordinates, but measurements. 1 hertz is enough data rate. Ponder that for a brief moment of silence here. Having said these things, I now must acknowledge one topic missing from all this: sharing of intent information. Covering that will require much more work. As always, advances in ATM will come by combining inputs from multiple sources. Navigation and tracking have much in common, but collision avoidance is different. I'm not trying to deny the importance of sat-nav inertial integration. My involvement in it goes back a few decades. References shown here offer details. For air-to-air tracking, I go back almost 5 decades. Today I'm just describing which approach applies to which function. TCAS used the limited technology of its time, but its collision avoidance capability is inadequate for dense traffic in air and non-existent on the ground. The approach needs to be expanded beyond sat-nav to include a wide selection of nav aids to apply the digital flight rules described by Captain William Cotton. This plan calls for action before ATM becomes even further outpaced by events.